All right, we're going to do our first day of related rates in this video. So related rates use implicit differentiation to be able to solve them. Okay, so we just learned how to do that by using the chain rule. So in this section, we are going to find rates of change with respect to time. Okay, so everything that we're going to be finding will be d something divided by dt. All right, dy over dt, dx over dt, dv over dt, dr over dt. Everything's going to be over dt because we're doing everything with respect to time and related rates. All right, so every related rates problem, you are going to be given a bunch of information. Then you'll be asked to find a specific piece of information at a certain time. And again, it's not going to be like, they're not going to say when t equals 4 or something like that. It's going to be at a specific time in relation to the variables you're working with. All right, so let's work one and we'll kind of see what I'm talking about here. Suppose y equals this, find dy over dt given that. So I always want you to write the given. All right, this is also things that we know, so I might write the word know instead. All right, so we know that dx over dt is equal to 2. And then we are asked to find dy over dt. That's our question mark when x is equal to 4. So that's when I'm talking about the when. Okay, it's when x is equal to 4. Okay, and so what that means is like, as we go through time, x and y are both variables. So they're changing from second to second, from nanosecond to nanosecond. They're always changing. Okay, and so what we're going to do is we're going to take a snapshot in time, and that snapshot's going to be when x is equal to 4 exactly. All right, what are the rates of change doing? Okay, and so what that means is like, I can't plug in 4 right now. If I just plugged in 4 for x right now, I would get a constant over here. Then when I take the derivative, I would get 0. And then every answer would be 0. All right, and that doesn't really make a whole lot of sense. Okay, so make sure that you take the derivative first before you start plugging any numbers in. Always take the derivative first. All right, so we're taking the derivative of this implicitly with respect to time. So the derivative of y is 1, but we're going to write that as dy over dt because it's 1 multiplied by dy over dt. So the derivative of y is dy over dt. The derivative of 5x squared is 10x. And we're going to multiply that by dx over dt. Derivative of negative 6x is minus 6. I'm going to multiply that by dx over dt. Okay, each one of these d something over dt's, that's the chain rule. We do the regular derivative, and then we multiply by the derivative of the variable. And the derivative of the variable is d, that variable, over dt every single time. The last one, plus 2, derivative of constant is 0. So we don't have to write anything for that. So this is our derivative right here. This is what we're going to plug stuff into. So you should be able to fill in everything you know, and that'll leave you with the one thing you want to find. So we want to find dy over dt. So that's our unknown. And then I should be able to fill everything in over here. So I have a constant 10. I know x is equal to 4. I know dx over dt is equal to 2. And sure enough, we filled everything in. So now I just need to calculate it and we're done. So that's 40 times 2 is 80 minus 12 is equal to 68. Okay, so this problem we did just in the math world. Most of the time related rates problems are word problems. So they're set in an actual physical world. We use some geometric equations that you're familiar with, and we will have units on our answer. Okay, so let's go into some more traditional related rates problems now that you kind of see how the mechanics of the problem work. Okay, so we have a balloon being inflated at a rate of 10 pi feet cubed per second. All right, so we're going to write down what we know. All right, so what I notice here, I really look at the units a lot. All right, we're even going to incorporate the units in our work on this problem. Okay, so feet cubed tells me that's a volume because it's a cubic unit, and then per second tells me it's a rate of change. All right, they even use the word rate right there for us. So this should tell you this is a derivative, and it's the derivative of a volume. So we're going to write this as dv over dt is equal to. Okay, now what they won't show you is a negative sign. That's going to be in the words. A balloon is being inflated, so it's getting bigger. So if a a measurement is getting bigger, then the rate of change is a positive rate of change. If a measurement is getting smaller, then the rate of change is a negative rate of change. So this one's going to be a positive 10 pi feet cubed per second. All right, so we know that. Now we're going to get to our find. All right, at what rate, there's that word again, is the radius increasing? So that's dr over dt, rate of change of the radius. All right, that's our question mark, and we want to find that when r is equal to 2 feet. All right, so they were generous enough to give us the formula for volume of a sphere. So we're assuming this balloon is a spherical balloon. All right, so we start with our volume formula, V equals 4/3 pi r cubed. And again, I don't want to plug in 2 for r right now because that would give me just a constant on this side. And if I take the derivative of constant, I get 0. And that's not going to be the answer, but most likely that's not the answer. And it certainly isn't going to be on this problem. All right, so let's take the derivative, dv over dt is equal to, all right, multiply by 3, that gets me 4 pi r squared, and then multiply by dr over dt for the chain rule. Okay, so again, you should be able to plug in for everything except for what you're trying to find. We're trying to find dr over dt, so I should be able to plug in my 10 pi, and I'm going to put in my units here as well. Feet cubed per second is equal to 4 pi times r is 2 feet squared times dr over dt. All right, so now we're just doing some algebra. So we need to divide. 2 squared is 4. 4 times 4 is 16. So that's 16. Dividing by pi, and then feet squared. I'm dividing by feet squared as well. So I do the same thing over here. 16 pi feet squared. All right, I'm going to go out to the side this time. So that's going to leave me with just dr over dt, which I'm going to write first, is equal to 10 divided by 16. Divide both by 2. 5 over 8. The pi's will cancel out. And then feet cubed divided by feet squared. The feet squared will cancel. The cubed will cancel, but we are still left with a single foot. And then we have our per second because this is a rate of change. Okay, so you do not need to put the units in your work every single problem. I like doing it on the first problem, maybe even the first 2 problems, to show you that the units work. You can do math with the units and they should come out right. But you can also just know what the units are going to be. Radius is a first power measurement, so it's feet to the first power. And then it's a rate of change, so it's got to be per a time unit. So feet per second in this one. And so you can just work out the math on the number and then just put your units on the end because you know what the units are supposed to be anyway. All right. Next problem is our ladder problem. Very popular related rates problem. So we have a ladder leaning against a wall that is 25 feet long. Okay, so I like to call that a true constant. The ladder will always be 25 feet long. It doesn't matter where we are in time. The ladder's size is not going to change. Okay, r equals 2 in this last problem was not a true constant because as the balloon expands, r gets bigger and bigger, or as the balloon, whatever the opposite of expands is, condenses, r gets smaller and smaller and smaller. Okay, so r is not a true constant in that problem. We were taking a snapshot at the moment r was equal to 2. That's when we solved the problem. Okay, but down here, the ladder's size stays the same the whole problem. Doesn't matter where we are. So that's a number you can plug in right away. In fact, I'm going to label my picture over here with 25 feet. All right, that is the length of the ladder. All right, if the foot of the ladder, so that's here, is being pulled away from the wall, okay, so that means that this measurement right here will change. So we need a variable to describe this side. I'm going to use x because it's horizontal. All right, it's pulled away from the bottom of the wall at 14 feet per second. At what rate is the top of the ladder, that's here, moving down the wall? So this is going to be a variable as well because it's going to be changing as this changes. So I'm going to label this with a variable, and we'll go with y because it's vertical. Okay, this is a right angle wall, floor makes a right angle. All right, so let's write down what we know. Okay, I'm not going to write the 25 because I have that in my picture over here. So if the foot of the ladder is being pulled away from the bottom of the wall at 14 feet per second, Okay, so that's this distance, but it's a rate of change, 14 feet per second. So it's the derivative of that. So it's dx over dt is equal to, and if I'm pulling the ladder away from the wall, that's making this distance longer. So it's a positive 14 feet per second. All right, what do we want to find? Okay, at what rate is the top of the ladder moving down the wall? So that is the rate, there's that word again, of change of this distance. So this is dy over dt, which is what we want to find. And then we want to find that when the top of the ladder is 7 feet, when y is equal to 7 feet from the ground. Okay, so this one, unlike the last problem, does not give you an equation. Okay, if they don't give you an equation, then they expect you to know that one. Okay, and so geometric formulas, they will almost always give you, unless it's like area of a circle that you're expected to know. But this one is not a geometric. Well, I shouldn't say that. You learned it in geometry, so it is geometric. But it's a traditional equation that like everybody learns. It's like the one thing that even people who hate math remember from math. Okay, what equation relates the three sides of a right triangle? Pythagorean theorem. So that's what we're going to use here. X squared plus y squared equals 25 squared. Okay, very important that you don't label this latter side with a z, because if it's a variable, then you have to do math with it. And it works. You can do it, but it makes it much harder. So we don't want to make the problem any harder. So that's why you want to make sure to plug in those true constant numbers early on in the problem. All right, so we don't want to plug in 7 though, because 7's not a true constant. All right, that's going to be, we're taking a snapshot, right? Right at the moment the ladder hits 7 feet from the ground, that's when we're taking this snapshot in time. All right, so we are going to take the derivative of this equation. So we get 2x dx over dt plus 2y dy over dt is equal to, this is a constant over here, derivative of a constant is 0. Okay, you can divide everything by 2, and that's just going to cancel out those 2's. Just makes our work a little bit easier. All right, now we should be able to plug in what we know and solve for what we want to find. So I want to find dy over dt, so that's going to remain a variable. I know that y is equal to 7, so I got my times 7 there. Okay, over here I know dx over dt is equal to 14. All right, I do not have an x. Okay, but I need to have an x, right? Because that can't be an unknown, because I already have my unknown right here. Okay, so think about it. Well, if y is equal to 7, let's draw another triangle over here. Okay, so we know the ladder is 25 feet long. And then if y is equal to 7, well, I should be able to find this other side. I know 2 sides of a right triangle, so I can use the Pythagorean theorem to solve for the third side. Okay, this is one you should actually know. It's a triple. So it's one of those fancy ones that has a whole number answer. Okay, like 3, 4, 5 right triangles, 5, 12, 13 right triangles. This one's a 7, 24, 25 right triangle. Okay, so that means x is equal to 24. All right, so do a little algebra. We're going to subtract the 24 over. And I meant to include my units, so sorry I forgot that. I'm going to put them in feet right there. This was in feet per second right there. And then 24, since that's measuring that distance there, will also be in feet. Okay, so I'm going to get 7 dy over dt. Trying to include my units, I'm sorry. 7 feet times dy over dt is equal to negative 24 feet times 14 feet per second. All right, then I need to divide by 7 feet. All right, let's see if we can do some simplifying here. So I'll end up with dy over dt is equal to, the feet here can cancel with the feet here. And then the 7 can cancel with 14, leaving us with 2. So I end up with negative 24 times 2, which is negative 48 feet per second. So the units are correct because y is measured in feet and it's the rate of change, so feet per second. The top of the ladder is moving down the wall, So the fact that it's a negative number because this is getting smaller, that makes sense as well. So I think that we have gotten the right answer here. All right, next one, we have a fish being reeled in at a rate of 2 feet per second from a bridge that is 16 feet above the water. At what rate is the angle between the line and the water changing when there are 20 feet of line out? Okay, so this bridge, 16 feet above the water, that is a true constant in the problem. True constant. All right, so what that means is like we can draw a vertical line here and we can label this 16 feet. We don't have to label this with a variable. All right, so we have a fisherman at the top of our bridge here, and the fisherman has cast a line out in the water. Okay, now that line, as the fisherman reels the line in or casts it out even further, that line can change. So we need a variable name for this. I'm going to call it Z. Okay, you can call it whatever you like. And then we have our water down here. And this line connects with the water right there. And this is where our fish is. So I'm going to write fish, and I'm going to write fisherman up here. All right, and then at what rate is the angle? So they're talking about an angle here. So that's going to be this angle between the line and the water, the line and the water. So I'm going to label this angle theta right there. Okay, and then also we have this horizontal distance we need a label for. So as the fish gets reeled in by the fisherman, the fish is going to get closer and closer to the bridge. So that's going to be a variable as well. So I'm going to label that X just because it's a horizontal. Okay, so let's write down what we know. So we know that the fish is reeled in at a rate of 2 feet per second. So that's the line. This line is getting shorter, reeled in at 2 feet per second. So dz over dt is equal to -2, because the line's getting shorter, feet per second. All right, what do we want to find? At what rate is the angle? So that's d theta over dt is our question mark. And then when there are 20 feet of line out. So z is equal to 20 feet. All right, so look at what you know and what you want to find. So we want to find theta, and we know about z. Okay, so I need an equation that relates theta and z together. Okay, so there are a couple options here, but there's one option that's much easier than any of the other ones. Okay, so I want to include the true constant. You always want to include the true constant in your problem. Okay, if you're not including the true constant, you can still do it most of the time, but you're going to make things much harder on yourself. So if I think about what can I do to involve theta with the true constant with the z, okay, it's looking a lot like a trig equation, right? If I do sine of theta, sine is equal to the opposite over the hypotenuse. That's what we want to do here. So sine of theta is equal to the opposite, which is 16, divided by the hypotenuse, which is z. Since we're taking the derivative, I'm going to rewrite this as 16z to the -1 power. Okay, so again, we don't want to plug anything in yet because we have to take the derivative first. So let's go ahead and do that. Derivative of sine is cosine theta, and we multiply by d theta over dt. Derivative over here, multiply by -1 is -16z, subtract 1, -2 power, multiply by dz over dt. Okay, I'm going to rewrite that, getting rid of my negative exponent. So I'm going to have my -16 on top, my z squared on bottom, multiplied by dz over dt. Okay, now that we've taken the derivative, time to start plugging stuff in. So I know that dz over dt is equal to -2. I know z is equal to 20. So this side will be -16 over 20 squared multiplied by -2. Over here, d theta over dt is my unknown. So once again, I have something I need to fill in for here. I got to fill something in for cosine theta because this is my only unknown. Okay, other thing before we figure out what this is notice I'm not using my units in my problem. This is one of those where the units don't really work out exactly with the math. So this is one that you'll just want to kind of work with the numbers only, and then you're just going to know what the units are, and I'll tell you what they are at the end. Okay, so we're going to draw another triangle here. And this is the triangle at our snapshot in time. All right, so we know that this true constant is 16. And then at our snapshot in time, z is equal to 20. Okay, so we should be able to find this other side over here. Okay, and it's another special one. So again, you can do the Pythagorean theorem, but you're going to be dealing with some large numbers, and it's usually easier if you can just recognize it. So if you divide this side by 4, you get 4. If you divide this side by 4, you get 5. And hopefully you remember a 3, 4, 5 right triangle. And so that would be, 12 over 4? So this side would be equal to 12 in this scenario. All right, now cosine, since this is theta right here, cosine is the adjacent over the hypotenuse. So you could go with 12 divided by 20, or you can do the reduced form of 3 over 5. Okay, let's do the reduced form of 3 over 5. So that's how you find your trig value. You find the other side of the triangle, and then you apply the trig ratio that you've learned. Okay, so now we need to solve for d theta over dt. So we are going to multiply by the reciprocal of our fraction to cancel it out. Do the same thing over here. Okay, so I get d theta over dt is equal to, all right, let's do, okay, I'm going to write it out kind of as a big fraction here. So I have a negative 16 multiplied by a negative 2 multiplied by a 5. All that's on top. Then on the bottom, I have a 20 multiplied by another 20 squared, multiplied by 3. Okay, so I'm leaving it like this because it's easier to start canceling stuff out. So like I can cancel out my negative with my negative. I can cancel out 2 with 20 and get 10. I can cancel out 5 with 10 and get 2. I can cancel out 2 with 16 and get 8. I can cancel out 8 with 20, both divisible by 4. So that would be a 2 right there and a 5 right here. Okay, and so that's all going to simplify to 2 over 5 times 3. So 2 over 15. Okay, this is a rate of change, so it's going to be per second, because that's what our other measurements were, right? Feet per second right there. And then angles in calculus are always measured in radians. So it's going to be in radians per second. There's our answer for this one. Okay, it's a positive value. So think about it. If we reel the fish in, okay, this line gets shorter, then the angle would get larger and larger and larger the closer we get to reeling it in. So it makes sense that this is a positive value. That angle does grow as the fish gets closer and closer to getting reeled in by the fisherman. All right, one more. Water runs out of a conical tank at a constant rate of 2 cubic feet per minute. Okay, so we need to draw a cone. So I'm going to draw a cone over here. Notice when I'm not given a picture, I'm always drawing one. That's a good strategy to use on these problems. All right, the radius at the top of the tank is 5 feet. Okay, that's a true constant. The tank's size will not change. So that is 5 feet. And the height of the tank is 10 feet. All right, how fast is the water level sinking when the water is 4 feet deep? So we have some water in here like this. Okay, and this is the part that does change. The water has a radius in feet, and the water has a height in feet. All right, and so the water level it's draining out. Water's running out of a conical tank here at the bottom, and it's going down. And so as it goes down, the radius gets smaller, the height gets smaller. Okay. This is one they would definitely give you the formula. So volume equals 1/3 pi r squared h. That would be given to you on this one. They don't expect you to remember that formula. Okay, so here's what we know. We know that water is running out at 2 cubic feet per minute. So that is a rate of change of volume. Cubic feet volume per minute rate of change. Running out, getting smaller, -2 feet cubed per minute. All right, we're trying to find how fast is the water level. Fast, rate of change of the water level, that's h. So we want to find dh over dt. That's our question mark, when the water is 4 feet deep. So when h is equal to 4. All right, so this one's a tricky one. We need to find an equation that relates v to h, because those are the only two variables we know anything about, v and h. Our formula has three variables. It has v, it has h, and it also has r. So I need to find a way to get r out of there. All right, so what we're going to do is do a proportion. You learned about these in geometry, and we're going to substitute something in for r. Okay, so proportion comes from our picture over here. So the whole tank has a ratio of 5 to 10, 5/10. Okay, and the water has a ratio of R to H, so R/H. Okay, and so we want to replace R, so we want to get R by itself. And so we can do that just by multiplying both sides by H. So R is equal to, reduce your fraction, 1/2 H. Okay, so I'm going to rewrite my volume equation. V equals 1/3 pi times 1/2 H squared times H. Okay, do a little simplifying here. 1/2 squared is 1/4 times 1/3 is 1/12 pi. That's h squared multiplied by another h is h cubed. All right, so now we have a formula in terms of v and h only, and that's what we wanted. All right, so now we can take the derivative. Okay, I think I might write it one more time. V equals 1/12 pi h cubed. Okay, so time to take the derivative. dv over dt is equal to, multiply by 3, we get 3/12, which reduces to 1/4, pi h squared, multiplied by dh over dt. Okay, you're going to plug in what you know. We know that dv is -2. I'm going to go back to putting my units in here because they work out this time. The angle one's really the only one where the units don't work out exactly. All right, then we have 1/4 pi. H is equal to 4. I did not put my units there, but that's in feet. So that's 4 feet, and that's squared. And then dh over dt is what I'm trying to find. Okay, I'm going to do one step before I divide everything. So I have my -2 feet cubed per minute over here. All right, 4 squared is 16. Divided by 4 is 4. So 4 pi feet squared dh over dt. Okay, now we can divide by 4 pi feet squared. And we should arrive at our answer. dh over dt is equal to, okay, -2 divided by 4 is -1/2. And then we still have the pi on the bottom. That's kind of weird. We don't see pi on the denominator very much, but it'll happen on these related rates problems sometimes. So -1/2 pi, and then feet squared cancel with 2 of the feet, leaving us with feet per minute. Okay, the units make sense because it's a rate of change. It's a first power measurement. Height is just a first power measurement. Remember, area is a second power measurement, and volume is a third power measurement. All right, and so I think we're good to go. Got our answer there. All right, so I'll see you on the next video for day 2. Hope you enjoyed that.